So I think we can start. It's my pleasure to welcome Professor Edward Lee to give a tech talk at Google today. Professor Lee is a Robert S. Pepper Distinguished Professor in Electrical Engineering and Computer Science in the department at UC Berkeley. His research interests center on design, modeling, and analysis of embedded real-time computational systems. He's the director of the 9-University TerraSwarm Research Center and a director of CHESS, the Berkeley Center for Hybrid and Embedded Software Systems, and the director of the Berkeley Ptolemy Project. He has a number of very distinguished accomplishments that I won't read through here, but today he'll be giving a talk on something that he's passionate about these days, which is the Internet of Things and the associated software around architecture around it. So I'll let Professor Lee take the stage.
Thanks, Shriram. I think we have a small enough group here that we can keep things very informal. So please feel free to stop me at any time with questions. There's no need to, kind of batch them up at the end or anything like that. Yeah. So as Shriram hinted, I'm going to talk about a project that is kind of near and dear to my heart these days, and I've been doing quite a lot of hands-on work on it myself, which is centered around software, and particularly, kind of an open architecture for the Internet of Things. And just to kind of set the stage, my focus, and I think, to be fair, our focus at Berkeley more broadly, is what I like to call the Internet of Important Things. A lot of people, when they think of the Internet of Things, they think of, Barbie dolls that are network connected, or toasters where you can print messages on your toast by uploading the messages onto a website, and things like that, which are sometimes of real questionable value. But our focus is really on things where what we're interested in, things that really matter from an economic perspective and from an industrial perspective. And I personally am particularly interested in safety critical things. And I think the idea of connecting safety critical things like factory automation robots to the internet is potentially a really scary proposition, particularly given the architectures that people are using today. So my focus really, it's worth keeping this in mind, that the focus is really more broadly on what we call cyber physical systems, which are integrations of physical dynamics with computing and networking. And I put IoT in the title because it's certainly the buzz these days. But the real heart of the intellectual problem is the problem of cyber physical systems and the problem of networking these systems. And it's not really that new of a problem. People have been actually working on this problem for decades. In fact, there's a variety of terms that have been used. And I think it's really quite recently that the IoT term has kind of galvanized the community. But not so long ago, IBM was talking about the smarter planet instead of IoT. General Electric was talking about Industry 4.0. Germany was talking about the industrial internet. GE AT&T was talking about machine to machine. Cisco was talking about the fog, which is a term that I really like. It's kind of like the cloud, but closer to the ground, so it touches the physical world. This problem has been around for a while. There's the buzz around it these days is a little bit of an overhype, I think, but it's worth keeping in mind that the trajectory is more long-term. Okay, so on software architecture, I'm going to just talk about two design patterns that are very commonly used in IoT applications. One of them is RESTful services, where you use, for example, HTTP to construct a query. You encode in the URL all the state information that needs to be provided to the service. So you have a client program, it makes some HTTP request, and then sometime later, it gets a response from the device or service, and the response will typically be handled using a invocation of a callback function, which these days in most of the software infrastructure that supports this pattern, this callback function will be atomic. It will be invoked atomically with respect to all of the other things that the software might be doing. Okay, so that's it's providing a concurrency model, and this concurrency model is pretty widely used. It's at the core of Node.js, which is used for server-side JavaScript, as you probably know. Vert.x, which is another server-side infrastructure, and it's even been used in embedded systems applications. So the concurrency model in TinyOS, for example, which is pretty widely used in sensor networks, also uses these asynchronous atomic callbacks as kind of the core of the concurrency model. So it's a pretty successful, pretty scalable model. It has problems, well-recognized problems. One of the problems is that because all of the callback invocations are atomic and mutually exclusive, you have to build your applications such that each piece of software that does some computation is short and quick. Because if you try to do something, long, heavyweight operations using these callback functions, you will block your application while those heavyweight functions are performed. So it can be kind of awkward to build applications this way, but for a lot of scenarios, it really works well, and it's certainly proven well in the marketplace, right? So an example of a use of this in JavaScript looks something like this. You require a package that provides your HTTP support. You construct a URL that encodes in the URL what you're talking to, plus some commands, plus some context information, plus some access tokens, plus whatever is needed to invoke the response. Then you invoke an HTTP GET at that URL, and you pass a function to this GET request, and this function will be invoked sometime later when a response has been received from the server. So this is a functional style of programming where you pass a function as an argument to the request, and then sometime later that function gets invoked when the request has been satisfied. So there's another very successful design pattern that is quite complementary to this one. The broadest term for it, perhaps, is actors. And the idea here is that your software components handle streaming requests. So you stream data through a service. Okay, so for example, if you want weather data, you might provide a stream of latitude and longitude data, and you get a stream of weather data back from that weather service. Okay, so actors embrace concurrency because they have a very different style. Instead of having the atomicity of the function invocation that these callbacks have, what you have is that each actor has its own data space, and the only way that these actors share data is through the streams. So as a consequence, actors can all execute concurrently. So you get a very different concurrency model from the asynchronous atomic callbacks, right? Instead of atomically invoked functions that are mutually exclusive, but maybe invoked very asynchronously, you have a whole bunch of pieces of software all running at the same time, processing input streams and producing output streams, okay? So the key idea in our software architecture that we're exploring is simply to combine these two patterns, okay? So we take the actor pattern, we combine it with the asynchronous atomic callbacks. So suppose, for example, that your weather service is obtaining data from a internet-connected weather station, okay? Then when this actor receives longitude and latitude data, it associates that with a URL for that weather station, makes a request. Sometime later, an atomic callback will be invoked, which belongs to this actor, and that atomic callback will then produce an output, a streaming response with containing the weather data coming back from that weather station, okay? So the idea now is that you can take advantage of both of these styles of concurrency and use them, trade them off one against the other, right? In some sense, your use of atomic callbacks is restricted to the design of a single actor. So there's the problems that you have of trying to keep actions short and so on can cease to be a problem altogether, because you can take your heavyweight operations and just put them in another actor, okay? And those can execute concurrently with the asynchronous atomic callbacks, because you only need to keep the atomicity of these callback invocations within the context of an actor, okay? So it's really, it's pretty simple idea, is to combine these two patterns, and yet it turns out to be pretty darn powerful and fairly rich. So we call this style of actors, we call them accessors, because really they're accessing services or devices, okay? And they're using this callback style to access those services or devices, but they're embedding that use within a streaming application, okay? So we're not alone pursuing this approach. The two projects I think that I know of that have gotten the most visibility, one comes from IBM, one comes from Ericsson. So NodeRed is an IBM project. Here's a screen dump of a NodeRed program. You can see that they provide a graphical syntax for instantiation of these actors. And Calvin from Ericsson doesn't have a graphical syntax. It's actually a textual programming language that you use to construct these accessors and interconnect them. So you know, we take this as somewhat of a validation, at least, that there is some interest in this approach beyond our own world. Yes.
Why is it a combination? I mean, aren't the actors atomic themselves? So what part of the atomic?
So the key here is that a straightforward actor model would be one where you have pieces of code that simply react to input data and produce output data, okay? The difference here is that we react to input data by making a request, which then the request will be satisfied asynchronously sometime later, okay? And that asynchronous response will result in the output data. Okay, so we're getting a combination of these two concurrency models, the concurrent composition of actors where you stream data through them, and the possibility of having many pending requests all out at the same time, okay, with asynchronous responses coming back, okay?
Where does the streaming?
So I'll get into the streaming quite a bit more, because that's how you do the streaming, it turns out, is really an important part of this architecture. But I wanted to sort of walk you through a potential concrete application scenario, and it's a toy scenario, right? It's inspired by this Google Home device that Sriram was kind enough to send me one of these a couple of months ago, and so I played around with it quite a bit. Okay, so here is what we call a swarmlet, which is a composition of accessors, okay? And let's suppose that this is providing a service in the next generation digital assistant. So this is a program. This graphical rendition is a program that runs on this device. Okay, that's the vision that we have. Okay, now what are the components of this program? Well, one of them is some application logic, which in our framework you write in JavaScript. Okay, so it's application logic that says, what do you want to do? Well, one of the things you might want to do first is talk to a user. Okay, so the application logic maybe produces some text on an output stream, and you route that text to a text-to-speech accessor, which uses this RESTful interface to access the Google Cloud platform, which will take a chunk of text and give you back a WAV file. Okay, get this WAV file back, and then you use a device accessor that accesses the hardware on the device to play the audio. Okay, it's just given the bytes from a WAV file, you play it for the audio. And then you turn on this capture device, which captures a snapshot of audio, and you send that back to the cloud, okay, which as a WAV file, which then gives you back text. You can then send that text again to the cloud, okay, to send it to a natural language processing engine, because of course the responses coming from a user are going to be unstructured text. And so you need a natural language processor. API.ai is one where you can program in applications, and that's going to do some analysis on the text, give you some fulfillment response, which you then send back to your application logic, which maybe then turns on a light bulb by using an accessor that invokes the Zigbee radio on this device. Now, this device doesn't have a Zigbee radio, but the next generation probably will, I hope. And this Zigbee radio will talk to the light bulb and turn the light bulb on. Okay. Now, that's a lot of technology to turn on a light bulb. But so this is why this is a toy application, right? But you get a sense of how what we're doing is integrating these streaming computations with these asynchronous atomic callbacks. Now, this particular graphics right here is actually constructed in this design environment that we call Cape Code. Here it is, okay? So these are accessors that we wire together in this graphical syntax, okay? And then we have this code generator that we can use to produce a chunk of code that can be deployed in a device that's independent of the graphical syntax. So this hue accessor, for example, will find hue light bulbs on your local network and give you control over them. This natural language processor, I actually wrote this, again, inspired by the Google Home that Sriram sent me. So it uses a JavaScript binding called API AI that you can download from api.ai. And it uses that to construct the requests for natural language processing, and then you can build in the logic for your natural language processing on the api.ai website. Okay, so I can't run this now because there's some pieces missing. I ran out of time to create the accessor for the text to speech, okay, and the speech to text. So I don't have that, but I have a slightly simpler demonstration application that actually I usually use this one for demoing because it doesn't require any network connectivity at all. So I can use it in places even where I don't have Wi-Fi. But it accesses a device on my local machine and a service that is also implemented on my local machine. And what it's doing is just taking snapshots of data from the camera and then processing that using a image processing application. And let me just, so this image processing application is looking for these patterns that are called April tags, okay, which are like QR codes, but designed to be much more easily recognizable in very noisy video conditions, right? So it's actually finding the April tags, drawing a little box around the April tag that it found, drawing a little circle at the center of the April tag, and then giving me a stream of outputs, which is the location of the center of that April tag. And in this case, I'm just displaying the stream. I'm not doing anything useful with that stream of data, but you can see how this combination of services and of streaming data and invocation of these callbacks is being combined in this scenario. Okay, so that's a real simple and very much a toy kind of application, but you get a sense of what we're trying to do, which is really to be able to compose services in this sort of complicated way. Now, just to talk a little bit about the code generation, right? We want to be able to design a service and then deploy it. So we'd like to put it on some future version of the Google Home that can host these swarmlets, right? So we have this code generator, and what the demo that I just gave you is actually running the code that the block diagram has in a Java environment using Java's built-in JavaScript engine, which is called Nashorn. And the graphical design environment is built on top of this system called Ptolemy 2, and I'm running it on a laptop. But that's not going to be how you're going to deploy something like this. When you deploy it, you're going to want to put it on to one of these smart gateways, okay, and have it become a service that just runs continually in the environment. And so we've in particular, we can deploy these to run, for example, on an Intel Edison or on pretty much any Linux-based processor. So we've been using these, what we call these swarm boxes here. But more interestingly, you can also deploy this because the generated code is actually JavaScript. You can deploy it in any environment that will execute JavaScript. So We can use Apache Cordoba to run it on an iPhone or a Google phone. Okay, although the iPhone stopped working with Cordoba fairly recently. I think Apple kind of decided their business model was inconsistent with running JavaScript on their phones. So I'm not sure what we're going to do there. But even more interesting, you can get these very lightweight JavaScript engines. One of the nicest ones out there actually comes from Samsung. It's called Duct Tape. And you can deploy onto really small devices that have, where you measure the memory in millibytes instead of megabytes, right? So we are very interested in being able to deploy these on small devices. And of course, since it's JavaScript, you can also deploy this to browsers. So the vision here is kind of write once, run everywhere. And of course, in order to get that to work, you've got to make sure all your drivers work everywhere, right? So for example, being able to capture video data from a camera is only going to work on some platforms, right? And where we are now, I would say, is a little bit like the early days of the web, where web pages would work in one browser and not work in another, right? And that's kind of where we are now. You can build swarmlets and they'll work well in this environment, but not so well in the Node.js environment, or vice versa. But over time, we expect these things to more homogenize and a sort of core basic infrastructure to emerge, as it has, for example, in the web.
So in the code generator, which part of it, does it only generate the JS part of it?
Yeah.
What part of the code does it generate?
What it generates is just JavaScript. And the JavaScript, it's JavaScript that describes the composition of components, plus the logic of each component, which is also written in JavaScript. Okay, so each accessor, its logic is written in JavaScript as well. Okay.
That thing is the cloud and all that. There are blocks here
Yeah. No, that's right. So the JavaScript just constructs the URL to make a request. Okay. The platform provides an HTTP access point, right? It's got to provide the HTTP service, right? If you deploy it onto a device that doesn't have any network connectivity, for example, it's not going to have the HTTP support, and you're not going to be able to access the remote service, right? But there's a sweet spot here where all of the access to the resources on the platform are controlled by the host that's installed on the platform, not by the application. Okay, so one of the things that I maybe didn't mention, but the application logic is run in a sandbox, and it's run as untrusted code on the platform. You don't give it access to resources, okay? Except the resources that you choose to give it access to. So if you want to give it access to the networking stack through HTTP, the host can do that, right? But the host can also prevent that access. So we're leveraging the experience with the web of being able to run untrusted code in an environment here, okay? It's one of the key reasons for choosing JavaScript as the language here, is because of the experience with the web.
So how is this different than just writing JavaScript?
Because if you write JavaScript for the whole thing, you have no streaming, okay? So you don't have that concurrency model available. You're building the whole thing in terms of callbacks.
You start programming with block until.
Well, you don't, yeah, but you don't want to write JavaScript by writing blocking code, right? You can do it, right? Most HTTP modules in JavaScript will give you access to a blocking HTTP request. But it's a really bad idea to do that, because it's going to block your application. And so it's really discouraged in JavaScript. You want to use these asynchronous atomic callbacks, right? But it's really difficult to build big applications that way, right? And to compose heterogeneous services. And moreover, in order to write low-level JavaScript, you have to learn each of these APIs. So you got to learn the API for the text-to-speech engine. You got to learn the API to access the audio hardware. You've got to learn the API to access the natural language processor, right? JavaScript doesn't give you any sort of convenient ways to package all that, right? And so this componentization of these services means I just can stream text to my text-to-speech processor, right? And I don't have to worry about under the hood how it's implemented, right? So you're kind of building applications at a higher level by composing services at a much higher level than you would if you were writing JavaScript programs.
Of course, the person who wrote that block gets
That's right.
It's now encapsulated in the cloud.
That's right. So the idea is we build up a library of these accessors over time, right? And you get then a rich ecosystem out of which you can build applications.
Sorry, I mean, it's just, but I mean, that would be like a normal function, right? That
Mhm.
would be one of those blocks.
Right.
So I guess, sorry for my ignorance of software, but again, why would it be different than writing a program that just calls?
It's really about a software architecture, right? The idea of streaming data through functions, through capabilities, rather than invoking functions, right? It's a very different style of design, right? And in some ways, that's, you know, kind of the potential blocking factor here. Programmers don't like new styles of design. That's a fact, right? And so, you know, part of this is mitigated by the nice graphical syntax, right? This is what NodeRed relies on, right? For example, you just you wire these things together and people feel like they're not writing programs. They are writing programs, actually. It's just a programming language with a different syntax, right? But it's also that this encapsulation of the functionality is being done at a level that's different from a procedure call API.
Okay, I guess
Right.
it's supposed to be the user, the interface and practice.
It's meant to be a big part of this. So a big part of what our objective is to make these kinds of capabilities, you know, the text to speech, the audio processing, the video processing, and all that, make them available to creative people who are not software engineering experts, right? They're just creative people, artists or whatever, right? So we really, it's part of making the IoT accessible, right, to creative
Also,
people.
I think the concurrency is harder to describe in a technical function. If all these things are happening concurrently, that would be harder. You can always do it using some threaded.
It's very hard to do it with threads, but I mean, very hard to get it right.
The concurrency would be that you get one request while the process, another one comes in.
Yeah.
All those paths are all.
Yeah. Yeah, basically, you know, in one of these applications in what we call a swarmlet, a lot of stuff is happening at once, and yet the logic is quite a bit simpler than it would be with a multi-threaded program. Now, this application, of course, I mean, this is an awful lot of complicated technology to turn on a light bulb, all right? That would be really kind of a problem to, you know, try to rely on this to turn on light bulbs. So how far are we from this Internet of Important Things? I mean, if we think of these, you know, these use of network resources as kind of a key idea behind the IoT, whew, this doesn't look like something I want to do, design important things with. You know, in fact, I mean, I was actually at a kind of a review meeting that I was asked to attend for an automotive company where they were asking for feedback on various of their research projects. And there was one project that was working on self-driving cars where all of the computing functions in the self-driving car were going to be done in the cloud. And my feedback was not very friendly to that. Okay, my claim was basically, well, I really hope that never gets out of the research lab. So there's a lot of challenges, right? I mean, these designs can be enormously brittle, right? APIs change, and you're relying on an API that's implemented somewhere else, and APIs do change, in fact. I tried to use Google's own API.ai API, okay, which is the natural language processing API. And there's a bunch of very nice tutorials online that enable you to get into this pretty easily. And those tutorials show you how you can actually give it audio data, but the tutorials don't work anymore, okay? Because you get this error message back saying that the speech recognition is going to be deprecated soon. You should switch to using the Google Cloud Speech API or other solutions, right? So, you know, even the documented API changes, and the reaction that you get from the cloud services will change over time. So a key question is, how do you design applications so that they can react reasonably to these kinds of changes and still be able to deliver some kind of useful service. So this is, in fact, a large problem. And I can't say we've solved it, but we've started to put in some of the infrastructure that we believe might enable it to be solved. The idea of accessors is that these are really chunks of code, and you can run this code untrusted. So you can download it from the internet, and you can substitute in new code on the fly. Okay, that's a key part of the idea. So we've been working on this architecture that we call a mutable accessor, which is simply that you define the interface, and then you provide search engines that can provide that can discover implementations of that interface in the local environment. So if you want to turn on a light bulb in a room, right, what you really want to do is search for an accessor that matches the light bulb interface and is in this geographic location, and then instantiate that accessor and turn on the light bulb. Rather than building in your application that it's this particular hue light bulb at this particular IP address, which is going to be a very brittle design, because as soon as that light bulb goes obsolete, or you give it away to your cousin and get a new one from a different vendor or something like that, then your application stops working, right? So this is part of what we can do by enabling this code to be very kind of sandboxed and downloadable and scripted, right? It's really borrowing this idea from the web. Safety and security are a big issue here, and privacy, of course. And we can see that, if you're relying on cloud-based services, you can be making yourself really vulnerable. Last November, much of the internet effectively became unusable in the US because of this distributed denial of service attack against DIN, which is this domain name service provider. And so any services that were relying on internet access at that point simply stopped working. And that's obviously going to be a problem if you're relying on internet access for safety critical devices. So Google themselves just last month got a lot of grief because they have this smart hub called OnHub, and it relies on Google servers for authentication. And without the authentication, it can't do anything. And that there was something went wrong with the connection between OnHub and the authentication servers, and it effectively bricked all these gateways so that everyone who had this as their Wi-Fi stopped having Wi-Fi and therefore stopped having internet connectivity and had to do a factory reset of the device and do the whole setup process all over again before they could get their Wi-Fi working again. So these are the kinds of problems that I think are inevitable when you intertwine your applications with services that are remote. I think one of the things that someone once told me that the definition of network computing is when a computer that you've never heard of has you stopped dead in the water. And it happens, right? So the question is, how are we going to deal with it? So I think that right now, a lot of the IoT activity is very cloud-centric. And I think that that is a tremendous source of brittleness in IoT services. And I think that that problem has to be solved really for IoT to really get beyond the hype stage and really take off, right? This idea that, even having the self-driving functions of the car being done in the cloud just scares the heck out of me. But a lot of the devices that you get out there come with their own little custom gateways. So this is reflecting the fact that most of the gateways that people have in their house don't have Zigbee radios, right? And so there's no particularly convenient way to talk to an energy constrained device that's going to have a Zigbee radio. We believe all of this is going to change. And in this TerraSwarm project at Berkeley, we've prototyped, actually 4 years ago, we built our own smart gateway device, which was a networking rich and somewhat computationally rich. I like to think of it as similar in capability to one of these devices, okay? But I call it an immobile because the key difference is it doesn't walk out of the room. It stays in the room. It becomes part of the infrastructure like your Wi-Fi gateway. Okay, but it has similar capabilities in that it's got Bluetooth radio, it can talk to devices, it's got this is a reasonable amount of compute capability and so forth. And so these are variously called smart gateways is what Intel calls them. Fog computing is what Cisco calls it. Edge computing, it's an access point with more than just a bit transport, service, right? So part of the idea here is that it's an access point on which you can run untrusted code to deploy a service, for example, okay? So how could you exploit these, for example, to improve security, for example, to prevent this OnHub problem? So I have one of my PhD students, Ho-Kun Kim, who, by the way, he asked me to let you guys know that he's graduating this year and will be looking for a job. He's done some pretty fabulous work on what he calls a secure swarm toolkit, which is the key idea is that it's locally centralized, globally distributed authentication, authorization, and security. So right now, pretty much all the authentication mechanisms that you see out there are centered in the cloud, okay? So he's trying to solve that problem so that you can have even isolated networks with state-of-the-art authentication on them. But of course, you don't really want these networks to be isolated. You want your swarm boxes to be gateways to the internet, so you can then have services that will bridge across these islands. So for example, you could have a swarmlet that accesses a local authorization service on a local edge computer or swarm box, okay? The authentication will work even if your internet connectivity is completely severed. So you can still use your devices on the local network, regardless of what's happening in the internet space. Okay, but of course you won't be able to necessarily interact with other devices that are not local unless you have internet access. And so to scale it up to the internet access, these local authorization engines, which he implemented as an open source authorization, it's like a public key infrastructure service, similar to the ones that are, supported by, these companies that you buy certificate licenses from. But it's a completely open source solution. And these local authentication authorization services then form a peer-to-peer network over the internet so that you can, in fact, get collaboration across the network while you've got network connectivity. But the key is to get this robustness where you can, continue to provide services on a local basis, even if things have failed on a more global basis. So the kind of applications that he has in mind are very much safety critical systems. So you have a swarm box on the car, which is mediating the accesses of all of the devices on the car to the network, okay? Those devices may be accessing a roadside system, such as a traffic light system at an intersection, which has its own swarm box with its own local authentication authorization service. This authentication authorization service is ensuring that people can't do what our colleagues at in Michigan did, which is to hack the traffic lights in the city of Ann Arbor to be able to control them. Ann Arbor has terrible traffic compared to the Bay Area, and so they felt the need to be able to change the traffic lights. So they figured out how to hack into them. But this kind of local authentication authorization service, this needs to work even if the internet goes down. Right? It's not acceptable for this to not work because of some denial of service attack, right? Imagine a denial of service attack being able to take down all the traffic lights in the city. That would be really, really problematic, to say the least. So anyway, so Ho-Kun's architecture, I believe, really can solve this problem. And it's a pretty nice and completely open source solution. Now, I'd like to spend the rest of my time, which isn't that much, just about 15 minutes, on the part of the problem that I personally find the most interesting, which is timing. I'm interested in Internet of Important Things, so these are often safety critical things like factory automation systems or something like that, where best effort timing is just not good enough. And you need to be able to provide some kind of guarantees. And the variability of accesses to the cloud is simply going to be too much variability. I'm not talking about average latency. I'm talking about variability, okay? It's the variability that is more of the problem rather than the average amount of latency. So let me talk about what I mean by timing problems. Well, let's look at the simple weather service. So this combination of streaming and asynchronous atomic callbacks has a potential problem, which is that you can issue a whole bunch of requests and then you can get responses in a different order from the requests that you issue. That can happen, right? You're sending these requests out to the internet, you're going to get responses asynchronously, they could come in a different order. That's just a simple example of a timing problem, and it's a timing problem that could affect your application logic quite substantially, right? You may, in fact, want to reorder the responses to ensure that the stream of responses is coming out in order as a stream of requests, or your application may not need that, right? It may be able to handle the reordering of responses without any difficulty. That's very much an application-specific thing, but it's a timing issue that you have to take into account in the design of the system. Okay? A more interesting timing problem is when you want to coordinate actions. So, for example, here's a little snippet of JavaScript code that sets up a function to be invoked periodically every 100 milliseconds. And another snippet of JavaScript code that is setting up some other function to be invoked every 100 milliseconds. Maybe in your application logic, there's a good reason why you wanted these two things to happen every 100 milliseconds. Maybe you really want these to be logically synchronous. So what you'd like is for every observer of these actions to see the effects of both function invocations. Okay? That's what I mean by a logical synchrony. So the kinds of situations in which this is really going to matter are things like factory automation systems. So this is a nice example of a kind of Internet of Things application, because this is a printing press from Bosch Rexroth. It's a huge machine. It's about like 4 times the size of this room. And it's got hundreds of microcontrollers on it. And paper starts out in 2-ton rolls that are about 2 meters in diameter. And the paper flies through the printing press at about 100 kilometers per hour. And the printing press is it's a print-on-demand service. So people upload their PDF files to a website, and this printing press prints the pages, slices the pages, binds the books, etc. Okay, and these cables are Ethernet cables carrying TCP/IP packets. All of the coordination of these microcontrollers depositing ink with 1 micron precision on paper flying by at 100 kilometers per hour is being coordinated over a TCP/IP network. They started shipping this product in 2008, and at that time, nobody in industrial automation was doing that, okay? They would use specialized networking technology for factory scenarios, okay? Like CAN bus, for example, is a very popular one, or various other variants that are out there that have temporal semantics in them. But nevertheless, they're able to get extremely reliable service out of this because they're able to control the timing. And in fact, they're running a protocol over TCP/IP here that synchronizes clocks for all of the microcontrollers on this network to extremely high precision, to precisions of a few nanoseconds. And then they regulate the use of the network so that you never get buffer overflows. So as a consequence, you never get the retransmissions of TCP. So you don't get the huge variability in network latencies that you would normally get from a TCP network, okay? So these kinds of networks are actually starting to become fairly ubiquitous. So time-triggered Ethernet, for example, is starting to get used pretty widely in industrial automation settings. And it's basically using internet protocols, but in safety-critical scenarios. And you have to be able to guarantee quality of service. Our focus is not so much on the networking technology, but rather on leveraging the networking technology, okay? And on being able to provide the software architecture that enables you to take advantage of things like high precision clock synchronization. So the idea here is that if you do, for example, in JavaScript, you specify that function F should be invoked every 20 milliseconds. Function G should be invoked every 40 milliseconds. Then we want, if these two are declared to be in the same clock domain, so we name the clock domains, If they're declared to be in the same clock domain, we want every observer, if it has seen an invocation of function f, it will also have seen an invocation of function g. Okay, so they're logically synchronous. Every observer sees them as having either neither of the two has occurred or they've both occurred. Okay, that's the key idea of logical synchrony. So you get this logical simultaneity of actions when you use these clock domains. So this is part of the infrastructure that we've provided in Accessors, which is a pretty significant increment over what you get with just writing straight JavaScript code. You don't get anything like this when you use timing functions in JavaScript, okay? So this is really a focus on interfaces, okay? So the key thing about Accessors is that there's actually two very, very different interfaces at work. And the interplay between these two interfaces is important. There's the streaming interface, the streaming data into an accessor and out of an accessor. And then there's the interface between the accessor and the service implementation, right? The requests that it makes and the responses that it gets back. The industry standardization efforts in IoT are almost entirely about this vertical interface, okay? There's all this stuff out there, MQTT, XMPP, AllJoyn, UPnP. The Industrial Internet Consortium is working on standardization efforts for this stuff. The IEEE Internet of Things committee is working on this. There's this open internet connection. Everybody's trying to standardize stuff here. And it's either standardizing things on top of HTTP or standardizing formats to use over WebSockets or standardizing the lower level network protocols by using CoAP. All of these are focused on the vertical contract. That's great. All of this has to happen, but actually it doesn't have to happen quite as much as you think. So here's a key idea in Accessors. Do we really need for all of the light bulb vendors to agree on an HTTP format for turning on a light bulb? I don't think so, okay? I don't think we do. Yet that's what these organizations are trying to standardize. But we don't need to standardize that any more than you need to standardize the way that your web browser communicates with your bank, okay? When you open a web browser and go to your bank, what happens? You download some JavaScript code, okay? And the JavaScript code runs locally in your browser as untrusted code, but it's running a proxy for your bank, okay? And then that JavaScript code gets to choose how to format the data that it sends to the bank. The banks don't have to standardize that. The vertical contract does not need to be standardized, okay? What needs to be standardized is the environment in which the proxy runs. That's what we do in the web. That's what has made the web so successful. The fact that it took many years to get there, okay, but we're there now. You can write JavaScript that will run in any browser, okay? And what that JavaScript is doing is running as a local proxy for a remote service. And the environment in which it runs is what got standardized. That's what we're doing with Accessors. The Accessor is a chunk of JavaScript that runs in a well-defined environment in the host. It reacts, the environment provides streaming inputs, and it can react by providing streaming outputs, okay? So we think of this as kind of a web-inspired architecture for the IoT. This horizontal contract, which is the mechanism by which the accessor interacts with its environment, is the one that industry is ignoring, okay? And the one that I think we're focused on, okay? So what is this horizontal contract? And here is where I think things really get interesting. So we have zeroed in on a particular way of handling this horizontal contract, which is not just streams, it's timestamped streams, because this enables us to get control over timing, okay? So the timestamps on the messages that flow between accessors play a critical role in the orchestration of the actions of the accessors, okay? So the way this might work, for example, is the accessor gets a timestamped request. It issues a request over the internet. Sometime later, an asynchronous callback occurs. That callback, when it comes in, will be timestamped. Okay, we can use that timestamp for various purposes. One of them is we can use it to prioritize responses, right? We can use it for health monitoring. Is that web service actually behaving properly? Are the latencies what I expect? If I need to adapt to degradations in the network, I can use the timestamps to determine that those degradations have occurred and so forth. Okay, there's all kinds of value in that. Now, if we can define this service, we can actually do even much better than that. We can actually get orchestration of actions over the network like you would need to do in this printing press. Okay, so the way that that works is that we can have an accessor that is actually providing access to another swarmlet that's running on some other device. So when I receive on this input stream a demand for service, I send out over the network something that produces in another accessor an output. That output then goes through the swarmlet logic to construct a response, which then comes back through this accessor through an asynchronous callback, which gives me a response here. If we can coordinate the use of timestamps across these networks, then we can orchestrate the actions across the network. Now it starts to get really interesting. So the way that we orchestrate the use across the network is an idea that, as with most ideas in distributed computing, you can find the roots of the idea in Leslie Lamport's work. So there's this paper way back in '84 where Lamport was using timestamped data in a distributed system to build fault tolerance into systems. So around 2008, we took this idea and adapted it to Internet of Things applications, really, okay, and constructed a programming model for time-synchronized distributed real-time systems. In 2012, a bunch of people from Google published a reinvention of the same technique under the heading of Google Spanner, okay? And the way Google Spanner does this is pretty easy to explain. So I'd like to explain Google Spanner's use of these distributed timestamps. How many of you know about Google Spanner? One person? Okay. So you can correct me if I got any of this wrong. But one of the key ideas is that if you have a distributed database, so you've got a bunch of data centers around the country, and they've replicated the data, and you'd like to be able to handle queries for the data in a distributed fashion. So you get for example, you're running an airline reservation system, and you get a query in Seattle to ask if a seat is available, and you get a query in Dallas that's trying to reserve the same seat. Okay, so the question is, what should you do? Right. Well, a brute force thing would be you have all these data centers communicate and form a distributed consensus about how to respond to those two queries. That introduces a lot of latency, a lot of network traffic. It's a very difficult thing to do in a distributed way. What you'd really like to do is have the data centers be able to respond without communicating. Okay, so in Google Spanner, what they do is they simply timestamp the queries. Okay, so if the query that came into Seattle is timestamped with timestamp T1, and the query that came into Dallas is timestamped with timestamp T2, then you define the responses to be dependent on the numerical order of those timestamps, okay? If T2 is less than T1, then the seat's available in Dallas. Otherwise, it's not, okay? That's the key idea. The numerical order of the timestamps defines what the correct response is for the database, okay? Very simple idea. You just have, but then how do you implement that, right? Because it sort of still seems like you have to form a distributed consensus because you got to compare a timestamp in Seattle to a timestamp in Dallas. Well, here's where you do a little magic and you synchronize your clocks, okay? If Dallas and Seattle have clocks that are synchronized and you can bound the error on the clock synchronization, okay? So you know that the clocks are not off by any more than E, some number E, okay? And moreover, you can bound the communication latency. So any data center that reserves a seat is going to have to broadcast a message saying, I've reserved this seat, okay? But there's a bound on the latency with which you're going to get that message. Call that bound B. Then Seattle Dallas, or well, whichever one is responding, whether the seat is available, just watches its local clock. I get a query, is this seat available? I watch my local clock. When my local clock exceeds the timestamp of my query, plus the clock synchronization error, plus the bound on the latency, I can respond without communicating with anybody, okay? And assuming that my clocks are synchronized within the error E and my communication latency is actually bounded by B, that will be the right answer, okay? So now I can get these coordinated actions without communication, right? It's a beautiful idea. Of course, things can go wrong. Your clocks might not be synchronized, your latency might be exceeded, in which case you can get out of order events, but these are always detectable because you will see a time-stamped event after you've already processed an event with a later timestamp, which is an error condition, okay? You know that one of your assumptions was violated, you treat that as a fault. So what we did was we applied this in the context of Internet of Things. We timestamp sensor data, okay? We use the timestamps as actuators. We interpret them as commands to perform an action at a particular time, okay? And we coordinate those actions over a network that is leveraging those synchronized clocks in order to get that coordination. So we get effectively a deterministic distributed real-time system. It assumes bounds on clock synchronization error, bounds on network latency. If in addition we assume bounds on execution time, then we can actually guarantee that actuators will in fact perform their action at the specified time. Okay, so now we can actually start to design the safety critical systems using this, where there's some closed loop feedback control. Okay, so a lot of assumptions there. I mean, you might not have synchronized clocks. So here's on the Berkeley campus, some non-synchronized clocks, right? Does it make sense to make all those assumptions? Well, you always make assumptions, right? When you write a piece of code and you run it on a piece of silicon, you're assuming a whole bunch of stuff about that piece of silicon. You're assuming it's not clocked at above some rate. You're assuming that the temperature of the chip is not above some threshold. There's lots of assumptions. And in the physical world, those assumptions may be violated, right? The assumptions are necessary for your model to be valid, okay? But that's always true with every engineering design. So we're just making the assumptions explicit. These assumptions about clock synchronization and network latency bounds are necessary anyway if you're designing real-time systems. You can't design a factory automation system without making those assumptions. So we're just making the assumptions explicit. And moreover, we've built a mechanism where you can actually detect the faults, okay? Whereas often with the mechanisms that you find out there that are more ad hoc, you're unable to detect the faults. Okay, so I think I've said all that. Let me just draw some conclusions because I've talked about a lot of stuff, some of it pretty quickly. First, IoT is not so new and it's not going to go away. It's not a flash in the pan. The term may be, it may be overhyped right now, but this is a long-term problem. And the broader problem is the problem of cyber-physical systems. The Internet of Important Things is the more interesting problem, I think, than the toys that a lot of people associate with IoT. There are modern concurrency models that are pretty useful, asynchronous atomic callbacks and actors, which have gotten a lot of traction and quite a bit of success. They can be combined. We've done that in this Accessors framework. But if you're trying to apply that to the Internet of Important Things, you need more determinism. And we can get that with these distributed time-based mechanisms. And I believe that we can actually get to the point where we can do safety critical systems using this kind of technology. So this work is happening in the context of this research center that we call iSci-Fi, Industrial Cyber-Physical Systems. These are the 4 key faculty who are involved in this. Prabal Datta, myself, Alberto Vincentelli, and Sanjit Seshia. So thanks, I will stop there.